Please join me in welcoming Patrick Haralabidis, a Google developer expert in AI and machine learning, cloud champion innovator and organizer of the Melbourne TensorFlow user group. Patrick currently leads the ML and software engineering chapter at Flybuys and has extensive experience in backend, mobile, cloud, and AI technologies. His passion for building technical communities and pushing the boundaries of emerging tech is truly inspiring. So let's welcome Patrick.
Hello, everyone. Thank you for this great introduction. Actually, sometimes it's hard for me even hearing people talking about me. So I should start and say by saying thank you so much for joining this session, or more importantly, for not leaving another lure of gadgets and that max input is quite high. So I guess in this session we're going to talk obviously about demystifying generative AI. But more importantly, what I want to do is I want us to cut through all the hype and explore the core concepts, tools, and all the other things that every developer needs in order to know more about generative AI itself. I hope that you will leave this talk feeling informed, inspired, and ready to start building the future with generative AI. Now, we will move through this content relatively quickly because we can't cover everything about generative AI in 30 minutes. But what I would like to do is keep this talk a bit more interactive. So at the end of each section, if you have a burning question, raise your hands, and I'll try to answer it. But more importantly, I'm going to leave for us enough, time at the end to ask any questions that you may have, even if they were not covered as part of this presentation. So really, it's all about you understanding things that you may have found difficult to understand before. So let's start a little bit with the basics. What exactly is generative AI? Well, simply put, generative AI is a subset of deep learning, a machine learning technique for building complex AI models. It's a type of artificial intelligence that can create new things. So instead of analyzing existing data, generative AI models can generate new data, whether it's text, images, music, code, or even 3D models. So take, for example, a look at this, right? This image wasn't created by an artist. As a matter of fact, I was able to create it in 10 seconds using imaging and a simple prompt, right? Or what about this code snippet? This whole function actually was generated by a generative AI model. So quick, so easy. But why should you care about it? Well, personally for me, I think it's important because generative AI opens a whole new world of possibilities. It allows us to automate creative tasks, build more intelligent applications, and solve problems in a way that we never thought possible before. Imagine, for example, automating the creation of a marketing copy, generalizing your own personalized learning materials, or even designing an entirely new product from the ground up with generative AI. The potential for me is actually quite transformative. And obviously, at the heart of many generative AI applications are large language models. So what are they? Well, they are powerful deep learning algorithms that have been trained on massive amounts of text data. This training allows them to understand and generate human-like text with remarkable accuracy. So, but unlike traditional AI models that are designed for specific tasks, LLMs are much more general purpose. They can be used for a wide range of tasks within the same underlying model, making them more versatile. But most large language models also tend to be quite multimodal, which is an architecture that allows them to use smaller, more efficient models to perform different tasks and bring that back to us. So I did promise for this to be a demystifying session, so let's start unpacking a little bit some of the terminologies that we use to describe models. And the first one is the little numbers that you see at the end of every one of those models. They may be something small, like 2B, or large, 70B. So these are not actually random numbers. They refer to the number of parameters that the model contains. So think of the parameter as the rules, the connections within the LLM that determine how it processes and generates language. They manifest as weights and biases And they are the ones that determine what the output of the model is actually going to be. Think of them as the secret knowledge of a librarian, right? That allows them to understand the relationship between different books and their content and their own domain. So the more parameters an LLM has, the more complex its understanding of language is. But just like everything in technology, there is a trade-off, right? The larger the number of parameters, the larger the computation requirements, the larger the memory requirements for running it. Well, parameters kind of like describe the complexity of the LLM. Tokens describe the breadth of knowledge. And they're not related to each other. They're completely unrelated. So tokens, which can range from words, subwords, characters, symbols, they basically signify chunks of text that the model processes. When you give an LLM text, it breaks it down into these tokens in order for it to be able to understand it. Yes?
Yes, sorry to interrupt, but just wanted to clear. I mean, so the parameters like transformative parameters, is that the actual count of the embeddings that models use? Or?
No, it's not. It's think of them as the I'm not sure if everyone asked the question. So is the number of parameters the number of embeddings? No, it's not. As a matter of fact, we'll talk about it a little bit later, but like it's more related to tokens, not with parameters. Parameters are the relationships, like when the models have, that has built internally.
Okay, yeah, thanks. Because I just wanted to
Oh,
clear
good.
this.
No, that's good. I'm glad that you asked. So the next, I guess the next thing that I want to mention is that when you normally see a model, right, that has a certain context window size. We hear that all the time. This really actually refers to the number of tokens that are supported as input and output limitations of on the LLMs. Gemini Pro, for example, supports 1 million tokens, which is impressive in a single prompt, right? And I believe there's a variant coming out that supports 2 million tokens. Okay, great. So, we understand now what they kind of like are, how, like what are some of the parameters that they use, but how do they work? Well, the answer is they use transformers. Wait, no, not these transformers. These transformers. So it is actually an architecture that was first introduced by Google in 2017. So there's a lot of background knowledge, a lot of technical stuff that go into transformer, and it's probably a separate talk on itself, but I want us to try and understand this a little bit on a high level. So LLMs work by breaking down what we talked about, tokens before, into, like as it's given to them into the context window itself. Now, imagine if you try to understand a sentence. You don't just read each word in isolation, right? You consider the context, the relationship between the words, and how they contribute to the overall meaning of that sentence. Well, this is precisely what the transformer architecture is really good at. It's capturing context and relationships between different tokens. Now, if we dive in a little bit deeper and take a translation example, within the architecture, the encoder takes the English sentence, "How are you?" and the decoder outputs the translation. But in reality, this actually happens across multiple layers and multiple relationships. So let's get a little bit more technical and try and understand this a little bit more. So first, the input text is broken down to tokens, right? I think we kind of like understand that. Then each token is converted into a numerical representation, which is the word embedding that we just mentioned in the thing. So think of embeddings of the word as converted digitally into something that the LLM can understand. It also captures its meaning in relationship to other words, right? The encoder keeps track of that word along with positional information so that it remembers where it is. And that is important because this is how we also understand the meaning within a language. Now here comes the magic really of this algorithm. The attention mechanism allows the encoder to weigh the importance of different words in relationship with one another. And this entire process gets repeated multiple times in different layers of the encoder, allowing the model to capture a really complex representation of the relationship between the words and the representation that they actually have within text. Oops, the other way. Right, so the second part of the decoder, the architecture is the decoder. So let's look a little bit at the workflow as well. Now, firstly, it receives the output that the encoder just generated, right? And then the decoder starts generating the output sequence token by token, predicting the next word based on the encoder's output and the previously generated words. Think of it like a writer composing the story sentence by sentence, building upon the previous one. Now, the decoder also uses the magic attention mechanism that we saw before, but in a slightly different way. It focuses on different parts of the encoder's output and the previously generated sequence to determine the most relevant information for generating the next word. If we were to take again the writer example, it's like constantly referring back to the nodes and the already written parts to make sure that there is consistency and coherence across the whole board. And then after the attention mechanism, the decoder passes that information through a mathematical layer and creates back a probability distribution over the vocabulary. This helps the model decide which of the word is the most likely candidate to output. It's like the writer choosing the best words, I guess, within the vocabulary to fit the story. So if we take away all the complexity, and I hope this kind of like sheds a little bit of light on that architecture, but you can summarize it as a process in which text is converted into tokens and embeddings with positional information, and then algorithms are applied to it in order to predict the most likely output out of this, the same way that we understand language. Now, okay, that works with text. But what about images and video and generation? Well, actually, this is one of my favorite AI-generated videos from Sora, right? Look at the detail, the stunning detail, even in the lighting and the reflection. It's really, really fascinating. So the architecture behind things, generating things like this is what we call a generative adversarial network. So or short as GAN. So I like to think of GANs as an art forger, trying to create counterfeit paintings, and then an art expert trying to detect them. That's the basic idea behind the generative adversarial network. Essentially, it consists of two neural networks in a constant battle. The forger that creates new data, and the discriminator, the expert, that tries to distinguish between real and generated data. And this competition between them actually is what pushes both models to improve and create results like the one that you have seen before. Okay, cool. Now we know what they are, we understand the parameters, we know how they work in terms of architecture at least. So how do we modify them? How do we go about that? Well, there's two different ways that we can actually do this. The first of all one, and you may hear that like throughout everywhere, it's the RAG, the retrieval augmented augmentation. Now, RAG is a framework that enhances the capabilities of the large language model by combining their existing capabilities with the ability to access and retrieve information from external knowledge sources. Now, this approach allows LLMs to generate more accurate, informed, and contextually relevant responses, right, overcoming the limitations that they may have from the original building. So how does a RAG work? Well, if you think of the flow, you have a question or a prompt that the user puts into the system, and then you have a retrieval mechanism, which pretty much retrieves the relevant information from the knowledge base or any external data sources that we have given to the model. This retriever could be like a search engine, vector database, or any other information system. Now then we have augmentation, which means that the retriever uses the information that it just took from the external source and enhances the original prompt with relevant information. And then, of course, this is fed back into the LLM, which with this new information is able to produce a more relevant response for this whole thing. So there's 4 key components that you kind of like can think of working within the RAG. It is the knowledge source, which is what we supply. Think of it as our own information. It could be a document repository or anything like this. The embedding model that converts those information into embeddings that we mentioned about before, so that the LLM can actually understand it. And of course, the retriever that goes out and does that kind of like communication between the two. And of course, and finally, the LLM that is responsible for generating the final response. So why should we use RAG systems? What is the value behind them? Well, first of all, we get a lot of improved accuracy, right? RAGs allow LLMs to accept up-to-date information. They're not frozen into the training time. And they allow them to also get domain-specific knowledge, leading to more accurate responses. We also have enhanced contextual relevance. By incorporating relevant content from external sources, RAG enables LLMs to generate responses that are more relevant to the user. You most likely have heard things like hallucinations, which is pretty much what the models does when they can't find information, they just give you a random response. So RAG is predominantly used for this as well. It reduces hallucinations because now it has a reference point. If it doesn't understand something, it can go into the source that we have actually given it to. And it makes it more adaptable, because when you have a large language model that hasn't been trained on your personal information, now you can use it in order to do this. So essentially, for me, the best place for utilizing RAG architectures is for things like question answering systems, where you need to provide those informations, or chatbots, obviously, that need to be built onto your own domain. Now, there's a couple of challenges with RAG systems. Mainly the first part is, well, maintaining your source of information and making sure that it's accurate and correct, because it impacts the system quite a bit. Choosing the right retriever in order to do that kind of work. And then, of course, you need to evaluate their performance, because you're changing the behavior of the original model. Now, outside of RAG systems, you probably have heard about the other approach that we can use to enhance models, which is fine-tuning. Now, I guess when you hear fine-tuning, we're really talking about the process of taking a pre-trained model and further training it on domain-specific data set, right? Most large language models today have a very good global performance, but fail in specific task-oriented problems. So fine-tuning enables the model to have a better performance for specific tasks, making it more effective and versatile in real world application. Now, this process is essential, right, for tailoring an existing model to particular task domain problem. And it gives us quite considerable advantages, actually, because now we have lower computation expenses, and we have the ability to leverage a cutting-edge model without building it from the ground up. Okay, so when we do fine-tuning, we have 4 different approaches that we can take in order to make that happen. The first one is supervised fine-tuning. And this is probably the most straightforward approach of all. So the model is further trained on large label dataset, right? A dataset that we actually have, which is specific to the task that we wanted to perform. Like, for instance, we would train our model on a dataset containing text samples with the corresponding potentially, sentiment analysis about our own organization. When that is not possible, when you don't have all that readily available information, another technique that you can use is what we call few-shot learning. And as the name suggests it, few-shot learning addresses that problem by providing few examples to the model during the prompting process. That's why we call them shots, right? Essentially, when you give him the prompt to the model, you also give it an example of a response of how you would like to do it. And then, finally, gradually make the model understand that a little bit more. Now, I've put there transfer learning, sorry. We're on the right slide. I put there transfer learning, but I think that all techniques that I described are part of transfer learning. This really, a technique is specifically aimed to allow a model to perform tasks different from the tasks that it was trained for. So, for example, if we have a model that is trained to recognize furniture, you can do transfer learning in order to make it understand completely different data set. And then the most important part, and why you would normally traditionally go into something like fine-tuning, is a domain-specific tuning. And this type of tuning tries to adapt the model to understand and generate text that is specific to a particular domain or industry. Right? So the model is fine-tuned on that dataset, composed of text from the target information. So, for instance, you may want to use it to generate a chatbot for a medical app. And that is the case because then the model would need to be trained on medical records in order to be able to adapt its language and its response to kind of like to that specific health field. So I'll take a pause there for a second. Do you have any questions?
Yeah, and sorry, I could be asking the wrong questions
All
here.
good.
So, yeah, so one of the things is, so, I mean, yeah, we know that the LLMs use those hidden layers to decode those based on the tokens. So, like, for an example, let's say, so there's this one prompt, let's say, which says that translate how are you in Chinese, and then there's another, give me a recipe for making a pizza. Is there change in the hidden layers that LLM decides, okay, so this is the translation thing, where I should be generating a Chinese sentence of this equivalent English sentence, and then there's this prompt for making a recipe for pizza, so I should be using a different kind of hidden layers. So do we know if LLM decides which hidden layers to use based on that one, and if it does, then how does it know which one to use?
Yeah, it's a good question. So I think maybe I went through a little bit, faster, but basically this is the whole, I guess, purpose of the transformer architecture. Right. So when you give it information, like in context, what the large language model does through this complex process there is to derive meaning, and then try to create the best response for that, right? That literally is well within that kind of like continuously iterative process. Now, obviously, every model has been trained differently. Every model, has its own different style and relevance. This is part of its own architecture, and of course, the data that it was driven, and that is what it will determine, whether it's performing well or not, into that kind of like scenario. But then, it's a nice segue to what we were just talking about. If it doesn't, those two techniques is where you want to go to.
Okay, so when we say it, then there's this black hole of LLM, which, okay, there's hidden layers, but we don't know what actually hidden layer does. Is that where the transformer comes? So, okay, so...
So the hidden layer that you're describing is a transformer.
Is the transformer, okay. Yeah.
So, and of course, enhance it, right? So then if it doesn't behave well, can you enhance it just with information? Then great, use a RAG. Do you need to retrain it to be better at something? Then use fine-tuning.
Got it. Thanks.
Yeah. Any other questions?
Any other questions?
Few.
I'll come back to you.
Hey, testing. Okay, cool. So sorry, this is going back a bit to the tokenization piece, where you take a sentence and then you convert it into these individual tokens. I was just wondering what the process is for doing that tokenization, because I think something that was interesting to me that it took one of the words, it was like demystifying, and then it took DEM as one token, and then Y as another, and S as another. I'm like, how does it make that kind of decision?
Yeah, that's actually a good question. So essentially we use models that do that. They also fall into the same kind of like process that we talk about the other models. So the model that created tokenization has been trained in large language corpus. So they have a reference of, of a really large vocabulary. And then what they do is they use their inbuilt vocabulary to try and translate, back into, a sentence into tokens based on their understanding. So selecting the right model to do that kind of like tokenization is important, because you may get the results like this, from words that they haven't seen. But most of the time they're quite good at doing that, really. And if we dive in a little bit deeper into the tokenization, it's not just breaking up the words, it's also removing things that don't make sense. Like, for example, in a sentence you may have things like the, or it, or it doesn't give anything to the large language model, right, in order to work with. It's irrelevant to its thing. Demystifying is probably the important thing in that sentence. Generative is probably the important thing, and that's what they try to capture. They try to capture the essence of the sentence and the key words, and then give that back into the model. Not everything in the sentence. So it doesn't really matter if they don't.
Sure, makes sense. Thank you.
Yeah, cool.
Thank you. Is there a technique that to achieve like greater performance in terms of like accuracy within like small number of parameters? Because if we see this graph, like there is a huge difference between like big model and small model. But I heard like some startups are trying to achieve much more to improve like performance within just a small number of parameters?
Yeah, that's a very good question as well. So again, everything will use transformer architecture. That's why I kind of like try to dive in a little bit deeper into it. So how well you build those layers within the transformer will pretty much determine how good the output is. What I want you though to take out of this is think that the number of parameters, the large number or the small number of parameters, is not necessarily related to the quality or to how well the model performs. Right, they're irrelevant, because if that was the case, then we'll build a 700 billion parameter model, and then I don't know, we have generative AI. It's not how it works. Those parameters, think of it as just generate a layer inside the model that gives it understanding, but then how it actually functions through its algorithm in order to use those layers to give you output, and the quality of the output is different. So yes, you can achieve really good results with a small number of parameter models. Like that perform quite well as similar ones. I think in one of my earlier slides, I had Gemma there deliberately, because although it kind of like only uses, I think, what was it, 27 billion parameters, it performs as well in quality as the 70 billion parameters of the Llama. So unrelated. So I understand that why they may want to do that, because they want to reduce computation requirements of the volume. But there's other things at play that can't get really into too much detail at this point in time that bring out the quality of the model.
I see. Thank you.
No worries. Any more? Okay, cool. Let's. I only have a couple of. I don't know how we're going with time. I have a couple more things to mention, and then we can kind of like resume maybe with questions. So now that we understand a little bit better, what we can do and what we can use. What are some of the tools that you can use in order to kind of like perform those kind of like two techniques that we talked about with your models? Well, there are a few ones that are my personal favorites. The first one is, this Hugging Face. And I probably want to start with that one. So Hugging Face is an incredibly popular open source library that provides a vast collection of pre-trained transformer models, right, now that we understand what they are, along with the tools to fine-tune them and to deploy them, right? It's a fantastic resource for getting started, so I would highly recommend that you do that. And what's included within Hugging Face is 3 key components. The first one is the Model Hub, which is a collection of all the models that you can utilize, and most of them are open source, right? So that means that you can utilize them easy. Then you have equally a dataset hub that gives you large datasets that you can use for those models. And of course, Spaces, which is a platform for sharing and deploying those machine learning demos and applications and allowing other users to interact with them. Another one of my favorite tools is LangChain. So we looked at ways that we can, so far, that we can work with a single model, right? We kind of like modify it. But what if you want to use more than one? Let's say, what if, for example, I wanted to use Gemini, because I like it for general language understanding, but then I also had a fine-tuned version of Gemma, and I wanted to combine those two within the same application to get, I guess, the one to do all the things. Well, this is actually where LangChain comes in. So it contains in kind of like 4 maybe different key components that you can see on the slide. And the first one is chains. And as the name suggests, right, what chains do, you create chains that allow you to combine different language models together in a sequential flow. So for example, you could chain a model that summarizes text with another model that does translation, and then get back a summarized translation of the whole thing. It also has agents, and I guess the agents, you can use them to allow an LLM to make decisions and take actions. So for instance, an agent could use an LLM to understand a user's request, search for the relevant information, and then either provide an answer or go out and do something else, called an API or a request or a response for this. Of course, prompts, but you can use prompts in large language models. The advantage that you get from LangChain here is that you can create templates for your prompts, and you can have them reusable and fully customized. And then finally, you also get access to memory, which enables you to incorporate really memory within your application, allowing the LLM to retain more information from previous interactions. And this is most of the time crucial when you're building chat applications or relevance, because you will need to have that context to go back into that. Another one of my my tools, I guess, is like, and that's good for experimentation, is Ollama. I will close with this actually, because this is an open source framework that allows you to download and run open source models on your own device without needing to go to the cloud or actually deploy something. It's a great tool for exploring, learning, and testing. And it's also very useful if, for whatever reason, you have a need to run a large language model that is disconnected entirely from the internet. So I would highly recommend it. So I will skip ethics because, well, we had such a fantastic talk before with Tanya, and I don't think I can actually do any justice to this. So maybe any final questions?
I have one.
Yeah, sure. Oh, good. No, I like questions. So, thank you.
Yeah, thanks. So, I mean, and just trying to be a bit more technical. So, I mean, they say that we have this generative intelligence, but we are moving towards AGI, which kind of like explodes everything. And we aren't there yet, but we are in that direction. In a very technical terms, as a developer, I just want to understand what does it take in the technical achievement to go to that direction to achieve AGI. So I mean, it's not like in general, okay, we'll achieve AGI, but what technically needs to be done to get that AGI, or just we are just running around those models.
That's a very interesting question, right? Like for I guess like for general intelligence, but I would probably say that more of the same. Like if you think about the way we kind of like progress now, we're adding capabilities to the models, continuously. Right? They're becoming better and better at doing what they're doing. But I think the problem with with I guess like general AI is that we don't even understand it quite well yet. Right? So it's very hard to kind of like put a roadmap to do that. I know that OpenAI kind of like had it as it's kind of like aspirational goal to kind of like help achieve that, but the how is not really a well-known thing. Like if we knew, we probably would have done it. Right? It's probably important to kind of like I think for me it's more important to think of like what are the implications and how do we do it safely and how we do it in a way that is kind of like meaningful and helpful. Because the resources that are required to know to do that are humongous, and the cost for doing these things is insane. So I wish I had the answer, but I don't.
I mean, so in the AI field as a developer myself, because what I think is like, as a developer, I mean, we all are pretty much constrained on the resources and everything in building models. I mean, as a developer myself, I definitely can't build 40 billion parameters of models. I don't think anybody here can. And all we can do at the moment is sugarcoat that models using RSE to make it a domain specific. That's it.
Well, actually that's a very good point.
Or if I don't know if I've misunderstood this AI areas, but what I think is like, for an example, if I want to make a practical application of a hospital, let's say, what I can do let's say for a disease recognition is use the model that either Meta builds or the Google builds or the Microsoft builds, and use RSE as on top of that as a sugar coating that one, and just feed in the prompt and get the output. That's all we can do, I think, as a developer.
That is correct, right? Yeah. That is correct. So I don't think the aspiration for anyone in this group or for any kind of like organization, right, should be to build its own large language model. That is not the point.
Exactly.
And that is actually probably the opposite point is the one that I want to make with this talk. Like as developers, as engineers, or anyone that is in, you have those models, and those models give you a lot of capacity and a lot of capability. So most of the time within organizations, we're trying to build solutions that meet our clients, our customers' needs, right? There's no need for us to invest that much. Yeah. What is important for us is to understand the techniques, like as we talked about today, right? So that when we talk about generative AI, we know the tools, we know the processes, we know how they work, and then we can utilize them in order to build what we need for our purposes. And I think that for me is more than enough. I can now build solutions for, like for our members at Flybys, or for, like for other organizations that it was not possible, like a few years back. And that is quite exciting on itself, right? And again, if you want to tinker, if you want to go into more things, there's open source models. They still give you a base, and you can keep expanding and building on them. So please do go out and use them. Yeah. Don't think of this as a restriction that you can't build these kind of like models. I don't think I even have an aspiration to ever build one.
Yeah, no, that's what I think as well. Because I mean, yeah, if you start going deep, like I mean, okay, you need to understand supervised learning, unsupervised reinforcement, and then you go to the maths behind how actually the transform. I mean, if you really want to understand the maths behind transformers, you get lost unless and until you are a super genius. So I'm like, okay, where are we going? Are we really building the model, or we are just paying Google for the model via API token and just sugarcoating that model and using the application on top of that?
Yeah, I think we're paying for a lot of stuff, but again, as I said, there's open source things as well that you can use if if you're very cost like sensitive, or that's not what you want to do. But again, start. I think for me the most important thing is, as you said, like now that you have a better understanding, hopefully I made a good job of understanding what the transformer architecture really is and how it operates, dive deeper, right? Go deeper. Now that you have a high level understanding of RAG or fine tuning, again, pick it up. What I wanted to do from this session is probably make everyone understand that when you see something in the news talking about parameters, tokens, context windows, those architectures, you understand what it actually is, right? And then you can safely navigate the whole space to go out as developers and build what you want to build.
Oh, good. We'll take one more question and that's it. We'll do a short one because we're running out of time. One more in the middle. Thank you. One quick one.
Hey, thanks, Mike. Just trying to understand from the outcome perspective, like the organic search is going down and users like us are using more of like perplexity and so on. How do you integrate the outcomes of service and products that you're building on this model closer to the user base, which the user are now on perplexity and so on, to connect your products and service closer to the users?
That's an interesting question. I think but that's also very hard to respond. That really depends on your organization and the strategy that they actually have, right? So I guess these are tools that help you build, like better products or better services for your thing. How do you normally do that, right now in your organization? We build mobile apps, we build websites, we build services, right? I think, like you can think of what we talked about today and generative AI as well as an enhancement onto that strategy. It doesn't give you a different approach on how you would bring those kind of like capabilities closer to to your users. You should enhance what you have, and I would kind of like go like that because it's it is too broad. Do you provide a search engine? Then yes, enhance your search engine with these capabilities. Google does it by default anyway. Right now, Google search is doing that. If you have a mobile app that can utilize generative AI, like for your purposes, add it. Make it available back into your customer base. I think that's probably the best answer that I can give because it is too broad. Yeah, thank you.
Thank you. Thank you so much.
Great. Thank you so much.
Thank you so much, Patrick. That was a fantastic session. Very interactive. Thank you so much, crowd. Your ability to break down such complex topics into such simple language is just beautiful.
Thank you.
Let's all give him another round of applause.